So in this class, I need us to consider our RC circuit as we are to work with our transient circuits. It is important that you do understand that you've got different types. We're going to consider the RC circuit, and another part, you consider the RL circuit, which is going to be for another class. So in this case, I need us to understand the formulas, the presentation of our questions. How are they going to ask the questions in terms of our RC circuit? Given DC voltage, which is as our supply, we're going to have our circuit of this nature. Let's say we've got our point A here, and also our point B, which is part of the switch that we're going to have. All right, so this is our DC voltage. So they are taken from a DC voltage. So this will be a DC voltage. Then we're gonna have something of this nature. Remember, this is RC. It's gonna be a capacitor and a resistor in series. A resistor and a capacitor. So that is the condition. So we're gonna have our resistor, capacitor, like that. So that is the presentation of our circuit, having this part to be our S1 representing our switch. So let's consider to say it is already closed. The voltage, we already have a voltage source, meaning to say we're going to consider the charging of the capacitor, this capacitor that we are given. It will be charged. It will be charged instant. We are talking about being charged in terms of instant value, instant. Remember your instantaneous values per time frame, per each time frame, a second, 1 second, 2 seconds. Is it 1 millisecond? It is being charged. This capacitor is going to be charging until it obtains the maximum voltage that is on the what? On the supply, which is our VDC. Approximately a maximum voltage is not going to be that exactly that is going to be given to a certain percentage. So that is the condition actually that is happening on a RC circuit. The moment you remove the source, meaning to say we are going to have the capacitor discharging. So source, having the source connected, it means you will be charging the capacitor. At that moment, you shall be charging the capacitor. Then having the source disconnected, you can have the source disconnected. In that case, we are talking of discharging. That will be discharging the capacitor. So the capacitor will then discharge. Like I said before, it is going to be referred in terms of a certain time, which brings us to what exactly are we referring to as the time constant of an RC circuit. Okay, considering this, because in your calculations, you are going to be given presentations for the time constant. So by definition, we can say that the time constant behaving on any, this is of an RC circuit. There we are considering an RC circuit, this one, because we are going to talk about it on another circuit, which is an RL circuit. So this is the definition for an RC circuit. May be defined as the time taken for the circuit to reach a steady state condition. Take note about this one. To reach steady state conditions after a disturbance due to that disturbance, now gaining to the steady state condition, assuming a constant rate of change in charging or discharging current. So whenever they talk about reaching a steady state condition, because they can ask you in an exam, calculate the time taken to reach that steady state. They are simply talking about the time constant. So they can ask that question in a hidden manner. So under an RC circuit, the time constant referred to by the letter tau, this one, that is tau. This one, Greek, remember our Greek letters, which is equal to the product of what? Resistance and capacitance, which is measured in seconds, dealing with an RC circuit. So this is the time constant. But in practical conditions that we deal with, practical situation, the time constant such a circuit is found to be the time for voltages and currents to charge by 63.2% of the voltage. Please be very, very careful about that, because this percentage that we are seeing here is important. Under exam condition, they can give you such a condition that maybe it's current or it's voltage that you are given. Remember, you are referring in terms of the voltage or maybe in terms of the current. Initially, your voltage, your maximum voltage, it can be 10 volts like that, okay? Then they can give you the voltage of a capacitor, maybe voltage 63.2% of this one. That is the one that we need, which is simply 0.632 times 10. So they will give us something like 6.32 volts as the voltage of the capacitor. By that alone, you are back to this statement. They are not giving you directly. They just give you a voltage. You see that, okay, this one, it means that we are simply referring to the time constant. Maybe they are asking you to calculate the time to obtain this voltage, the time taken. You know that that time taken is the time constant, guys. They are saying in practical, it is going to be at 63.2% of the voltages and the currents. So once you see your values at 63.2%, or once you see these values, maybe it's current that you are given, I as 6.32 amps, but the maximum current that you had before, it was maybe 63.2%, whatever that amps that you had. But you see that it's a certain percentage of that value that you had before. As long it gives you a certain percentage of that part that you had before, which is what? Which is at 63.2%. As long it is giving you that. The time there is the time constant. So it's another definition that you can use in a practical condition, in a practical situation. So after that, after a time period equal to 5 times, which is 5 time constants, the change in voltage and current is at 99.33% of the total change, meaning to say it is not exactly at 100%. So it's going to be approximated to 99.33%. So this is the illustration that we are seeing here of our time being equal to 5 tau. After a time period, it's going to be equal to 5 tau. So meaning to say, in that case that you've calculated your tau, in terms of the time, your time is going to be equal to 5 tau. As long it is of what? At time constant condition. As long it is at time constant at 63.2%. Okay, so we shall actually have exam condition that relate about this formula. Considering your RC circuit, it is very, very important that you understand, especially these percentages and the definition. And that your time constant is resistance times capacitance measured in seconds. So this is what we have as we consider our circuit. We're going to see that it's going to be having a charge and discharge, which you're supposed to know in terms of your voltage. Let's say this is our maximum voltage. Then this is negative. We're just going to have a charge and discharge. So on a charge, we are going to have our voltage decreasing. Okay, so it's going to be like this. While at least on a discharge, it's going to be a vice versa, an increase in terms of our voltage. And this will be reflected with a negative approach. In this case, it will be increasing, a reflection there. So, okay, this is, you just need to know your diagrams, guys, as usual, this and that. But in your revisions, you need the formulas. Now, as I said before, with that time constant, that one, I spent my time explaining it, because you see, there are questions that disguise on that. So you must be very, very careful on understanding your time constant, this part that I was explaining. Gonna see, like I said, approaching our question papers. So for the formulas or for the calculations that you are going to actually have dealing with an RC circuit, we are going to consider the part of charging. When you are charging the capacitor, meaning to say the source is connected, the VDC is connected at that moment. When it is connected, we can calculate the voltages. Remember, there's a capacitor, there's VC, the resistor, there's VR, the current. Remember, I said the VDC actually will be equivalent like to the maximum voltage that you are referring to. So during the charge cycle or during the charging cycle, this one, just going to consider like our charging cycle, the voltage across the resistor, VR, is given from the voltage VDC or maximum voltage that you'll be given. And this will be e to the exponent of minus t over tau. So it depends with your textbook, guys, the one that you are using, how they present this. Some textbook was tau. Remember, I said when it is of a capacitor, remember that. Okay, so here we must remember that tau is equal to what? RC, RC circuit. So some textbooks, instead, they can remove this tau and represent it with RC. So they will give you a formula like VR is equal to VM e to the exponent of minus t over RC. Instead of them writing tau, they'll write it as RC. So it's up to you guys. Okay, but that tau there represents RC. So it's one and the same thing. So you can just use it that way, or you can calculate your tau on its own. Then you substitute it there, which is the best way that I need us to just understand. So this is our voltage across the resistor in volts. Number two, we need the voltage across the capacitor, which is VC. During the charging cycle, that is going to be VM into 1 minus e to the exponent of minus t over tau. That is during the what? During the charging cycle. All of these formulas that I'm writing here are of the charging cycle. So this is what you're going to have, T over tau. So that's our VC. Then the current, which is taken at an instantaneous condition, is going to be taken from the maximum again, which is the one that you have from the VDC and the resistance. So you're going to have the current there, which is Im e to the exponent of minus t over tau. So as we can see, that is the effect that we're going to have. Our VR and the I there, they go hand in hand, like in this part of the exponential, this one, whereas the VC is the one that is going to have 1 minus. Okay, so this is of the charging cycle, where in this case, where this current Im can be calculated because it's the current that we can have because of the resistance value, but considering to Vm. So it's going to be Im is equal to Vm over what? Over R, which is our Vm is that VDC, the maximum that you are given at a certain condition that is there. So guys, as we can see here, this is voltage written in terms of T, because this is going to be replaced with a certain value. T can be a constant. I mean, T can be a value that does not have a substitute at a certain condition. Not to say it's a constant. No, not to say it's a constant. It can be a value that we do not have at a certain condition. Like maybe let me just write it as I is equal to 2 e to the exponent of minus t. Maybe our tau is 3 or something. We do not have t. We can calculate t. We're going back to our logarithms, back to our mathematics. We can calculate t. But I want you to see something that is presented. It's as the current in terms of time. So meaning to say, as we are given these 2 and 3 as constants, we can also do the same thing to say, let this be a constant for now, and let this be a constant for now. It means I is written in terms of what? In terms of t. So if I is written in terms of t, they can ask us for the rate of change. Guys, you are given VR in terms of t, you are given VC in terms of t, you are given I in terms of t. From that, you can be asked the rate of change. Remember your mathematics. When we were in mathematics N5, when you had the rate of change, dVR dt, meaning to say the rate of change of this VR with respect to time. VC, dVC over dt. In terms of current, di over dt. The rate of change. The rate of change. Whenever they ask you about that, the rate of change, what are they asking? Is it voltage? Voltage per second. Current per second. Amperes per second. Volts per second. That's the rate of change. So it is going to depend from what you're given. So if it is I written in terms of t, the rate of change is supposed to be for the I dt, current with respect to time. Meaning to say, the answer is going to be in terms of time. This one is going to be in terms of t. So if it is in terms of t, you can substitute now the value of t that you are given. Is it the rate of change of time when t is this? Is it the rate of change of, there is the rate of change when time is, the rate of change of current when time is this? You substitute that current that you are given there. So sometimes they can say initially, the initial rate of change. Whenever they state something like that, to say the initial rate of change. What, guys, what is important is here. Rate of change. There is a rate of change. Meaning to say we are going to apply our DIDT. But in that, they are saying the initial. Where are we starting from? Initial, meaning to say the time must be equal to 0. Initially. At the starting point. Initially, t is supposed to be equal to a 0. Initially, when you are starting, our starting condition to say it is charging, you're starting to say 0. That is initial. So initially, your time, you use it as a 0. But this part is not going to change to say the derivative of v with respect to time. The derivative is not going to change. That part is not going to change. So meaning to say, as you consider your derivative, let's just do an example here, just to find derivative. I want you to refer back to your mathematics, guys. Remember your mathematics. Let's just talk about this one. The rate of change of current. Rate of change. The rate of change of what? Current. Just want you to see something here. This is given as I is equal to Im e to the exponent of minus t over tau. So remember the rate of change, we're talking about di dt. Di dt, rate of change. Rate of change with respect to time. So if it is di dt, meaning to say we are differentiating with respect to time. With respect to time, this one, t. So if it is with respect to time, what does it mean? It means I am this one. And these tau, they are constants at that moment. We are not relating to them. They are just like numbers there. Okay, let me bring you back to your N5, guys. N5 mathematics. I is equal to, you put a number here, 2 e to the exponent of minus t over 5. And you're asked to differentiate the IDT, guys. This you can differentiate. Remember, E remains as it is, but you're supposed to differentiate this. You're supposed to differentiate this. Remember, this is the same. This presentation that we are seeing is same as 2 e to the exponent of minus 1 over 5 times t, like this. Minus 1 over 5, like here. There's a minus 1 over here. This one. Minus 1 over 5 times what? Times t. So meaning to say, If you differentiate, you are going to drop this one to multiply the 2, and it gives you 2 times minus 1 over 5. So it will be minus 2 over 5. E to the exponent of minus 1 over 5t. As it is, just remains as it is, but you have to drop the exponent that is affecting t, this one that is affecting time. So if you consider that in this present, you will see this is what we have here. This one, the minus 1 over tau, this one, the minus 1 over tau, we are going to remove it. This is our constant, the whole of it. So we're going to take the minus 1 over tau as it is. So I hope you understand what I'm trying to say there. We're going to take this minus 1 over tau as it is. This is our constant. So we have to drop that exponent down. So by dropping this down, it is going to be, it was supposed to be Im times, because you drop this down, it multiplies. So it's going to be times minus 1 over tau like this. You dropped exponent, the derivative with respect to time, this one. Just like this one, minus 1 over 5. You dropped this one 2 times minus 1 over 5. So it's the same, Im times minus 1 over tau. So it will give us minus this one, multiply this. So it's going to be minus Im over what? 1 times tau, which is tau. Just like that. Then the E, remember, it remains as it is. So the E here is going to remain as it is. E to the exponent of minus t over tau. Guys, this is, you have differentiated. The moment you differentiate, this is now called the rate of change of current. So if they say initial t must be equal to 0, meaning to say the whole exponent here is now a 0. You substitute Im, you substitute your tau. Your answer will be amperes per second. If it was from V, your answer volts per second. So it depends. So it's just whenever they talk about the rate of change, think of your derivatives. So you're going to see that in examples, but that is the major part that I want you to understand as we are going to be having our examples in our next class. So make sure that you do understand that they can ask you questions about the rate of change. All right, let's move on to another part of our calculations, which is now when this capacitor is discharging when the source is disconnected. So as part of our calculations, remember, we talked of the charging cycle. That was the first condition. So during a discharge cycle, so you're going to talk about a condition where there is a discharge. So during a discharge cycle, remember, the source is disconnected now. Source disconnected. The moment you disconnect that, the capacitor starts to discharge. Remember, the capacitor, it will have charged to a value equal to Vm according to theoretical values. They will be saying your capacitor is charged to a value equal to Vm. In that case, also, before we talk about this, let's go back to that condition of Vm and this Vc and Vm. Remember, we are relating the capacitor and the maximum voltage, which is your DC voltage there. So they can ask a person like the capacitor voltage to rise to X%. They can ask something like that. Let's just say a simple part. I almost forgot to put this one into consideration. Something like this. Capacitor value. The capacitor voltage, actually. I'm going to talk of the capacitor voltage to rise to X% of final value, of the final value, which is the final voltage. What does it mean? X%, maybe it's 20%, 30%, 40%. The capacitor voltage to rise to X, the percentage given, but of the final value. They are saying Vc, which is your capacitor voltage, will be equal to X% of what? The final, which is your Vm. That is what it means. So you can calculate your Vc from there. So if it is 5%, it's going to be 5% of what? of VM, 5% of that. Unless it is at a condition now when they are saying it is at 63.2%. There you know the time that you're supposed to calculate is the time constant. I talked about that. Okay. Anyways, like I said, guys, let's just hold on for our questions for now. But you're supposed to know that there are questions like that. So let's just know that. On a discharge, number one, our VR is going to change the way that you calculate it. Is going to be this VC. I mean, the VC is going to change this one. It's the only part that is going to change your VC, the presentation. The rest will be as they are. So the VM, which is our VR, is going to be as it is, VM e to the exponent of minus t over tau. The VC, like I said, the VC is the one that will change. So the VC will be presented the same way as we are presenting our VR as VM e to the exponent of minus t over tau. So if you check for a discharge, there is nothing that has got a bracket like this on a capacitor. Even the I there that you're going to calculate does not have a bracket, but that will be a negative. All right, so this one, you can put a negative here, the guys, sorry for that. You're going to have a negative there. All right, then also on the current, it's going to be I equal to, and also have a negative there. All right, that's a discharge there. So this will be IRE to the exponent of minus t over tau. Now it is a discharge that is considered. This is current measured in what? In amperes. So they can ask questions like that during a discharge cycle. You just need to understand these formulas and also to consider whether it's a charge or it's a discharge. They can also ask us about the energy stored in a capacitor. All right, so the energy stored in a capacitor. That's another part which is also important for you to understand. So we do understand energy. We use W like in our normal presentation, but you see that they'll be using omega depending with your textbook. Okay, so the one that I'm using, they use omega, which is 0.5 CV squared, which is the capacitor voltage. This one. So you take the capacitor voltage that you are given. So please be careful. When I'm saying you take the capacitor voltage here, if the capacitor voltage at that moment is equal to Vm, you use it according to the condition that you are given. Is it a full state that you're talking about where now the capacitor voltage is charged to Vm? It means the value there that you use is what? Is Vm. But the actual condition is supposed to be the voltage across the capacitor. So you relate that voltage across the capacitor to the condition of the question. How is the question presented? How is the question now presented on that part? All right, so that's it, guys. I talked about the rate of change questions, how they're going to ask them from this. So let us just try to work as much questions in our revisions. So we'll see in our next class having examples on what we have just referred to in these formulas.